In this lecture, we'll discuss about the transient response of series RL circuit for DC excitation. So before that, we'll discuss what is transient response. A transient response of a circuit is a temporary change in the way that it behaves due to an external excitation. Okay, so this is a temporary change in the behavior of the circuit. So this will disappear with time. So on off or off on mode changes of the switches or sudden changes of the excitation, that is the voltage or current source modeled as a step functions or the major causes of the transients. So in short, the response of a circuit containing resistances, inductances, capacitances and switches due to sudden application of voltage or current is called as transient response. So here we are going to discuss about the transient response of series RL circuit. So in series RL circuit we have two different types. A series RL circuit in which an active source is introduced after transition is called as driven series RL circuit. Transition means switching on or off. A series RL circuit in which an active source is absent after transition is called as undriven series RL circuit. So let us consider a series RL circuit as shown in the figure. Here R and L are connected in series across a switch. So here DC excitation voltage is provided. So whenever the switch is closed, this DC voltage will get applied across this R and L series circuit. Hence it is called as driven series RL circuit. So let us consider I of t as the current flowing in the clockwise direction. Okay, so now let us assume that at t is equal to 0, the switch is closed. Okay, transition means initially the switch is kept open. Now at the instant t is equal to 0, the switch is closed. So once the switch is closed, the voltage will get applied across the R and L series and the current will start flowing. Okay, so before transition, that is before closing the switch K is kept open for a very longer interval of time. So now if our aim is to find out the transient response of driven series RL circuit. So that means we have to find out the expression for the current through the inductor for t greater than 0. So before that we have to find out the initial conditions. So let I naught be the initial current flowing through the inductor. Okay, at t is equal to 0 minus up. So 0 minus is nothing but the instant just before closing the switch. So we have assumed that at t is equal to 0, switch is closed. So just before closing the switch is kept open. So whenever the switch is kept open, the voltage will not be applied to the RL circuit and hence the current will be 0. So hence the current flowing through the inductor is also 0 at the instant t is equal to 0 minus R. So inductor has a property, it will not allow any sudden change in the current. Okay, so the current through the inductor cannot change instantaneously. So therefore we can write I of 0 minus is equal to I of 0 is equal to I of 0 plus is equal to 0. So I of 0 means it is the instant at which switch is closed. So I of 0 minus means it is the instant just before closing the switch, and I of 0 plus means just after closing the switch, immediately after closing. Okay, this is immediately before closing the switch. So this is let this be equation number 1. So now for all t greater than or equal to 0 plus the switch is closed. So now we can draw the equivalent circuit as shown in the figure. Now if the switch is closed, this voltage source will get applied across the RL series circuit. So I of t is the current assumed. Okay, it is flowing in the clockwise direction. So now we have to apply Kirchhoff's voltage law. So we know that Kirchhoff's voltage law is nothing but sum of the voltage rise is equal to sum of the voltage drop. So voltage rise is with respect to voltage source, and voltages across resistors and inductors are considered as voltage drop. Okay, so here voltage rise is V. Okay, because the current direction is from negative to positive. So if the current direction is from negative to positive, then the voltage is defined as a voltage rise. So this voltage rise will be equal to sum of the voltage drops, that is voltage drop across the resistor plus voltage drop across the inductor. So voltage drop across the resistor is given by Ohm's law. V is equal to I into R. So here I of t is the current, R is the resistance value, plus voltage drop across the inductor is given by L into di of t by dt. So let this be equation number 2. So our aim is to find out the value of I of t, that is the transient response of the DC series RL circuit. So now we are going to divide this equation number 2 by R and rearranging the equation. So if we divide this equation by R, we'll get V by R is equal to, here if we divide R and R will get cancelled, so I of t plus L by R into di of t by dt. So this can be written as L by R into di of t by dt is equal to V by R minus I of t. So this is equation number 3. So now we are going to separate the variables in order to find out I of t. Okay. So this is the previous equation. So now we are going to cross multiply this equation and rearrange it as ti of t divided by V by R minus I of t. So this term is brought down. So di of t divided by V by R minus I of t. So this term can be taken towards the right hand side. So R by L into dt. Okay, let this be equation number 4. So now we are going to integrate this equation on both sides. So already we know the integration formula. Integral of dx by x can be written as ln of x. Okay. So this differentiation of x lies in the numerator. So in a similar way, the differentiation of this denominator term lies in the numerator here. Okay, v by r, differentiation of v by r is 0. Differentiation of I of t is di of t. So this can be written as minus ln of v by r minus I of t. On the right hand side we have r by L is a constant term. Integral of dt is t plus k dash. K dash is a constant term. Okay. So now we have to find out the value of k dash. So in order to find out the value of k dash, we are going to use the initial conditions. So already we know the initial conditions, that is I of 0 is equal to 0. So this is the initial condition. We are going to apply this condition in the equation number 5. So we are going to replace t with 0. Okay. So at t is equal to 0, I of t is 0. So we are going to substitute 0 in place of t. So here this will become I of 0, here it will become 0. So k dash can be written as minus ln of v by r, because I of 0 is 0. So we have found out the value of k dash. So let this be equation number 6. So now we are going to substitute this equation number 6 in 5. So fifth equation already we know. So fifth equation is minus ln v by r minus I of t is equal to r by lt plus k dash. So now if we substitute the value of k dash, we will get minus ln of v by r minus I of t is equal to r by L into t minus ln v by r. Okay. So now we can rearrange the equation in order to obtain I of t. Okay, taking this term towards the right hand side and taking this r by L minus t towards the left hand side and rearranging, we will get ln v by r minus I of t minus ln v by r is equal to minus r by L into t. Okay. So we already know the formula, ln a minus ln b can be written as ln a by b. So this is in the form ln a minus ln b. So this can be written as ln v by r minus I of t divided by v by r is equal to minus r by L into t. Okay. So now we are going to take anti-log on both sides. So if we take anti-log, this log term will get cancelled, and here we will get e power minus r by L into t. Okay. So this equation can again be written as v by r minus I of t is equal to v by r into e power minus r by L into t. So now our aim is to find out I of t. So we can directly get I of t from the above equation. So I of t can be written as v by r minus v by r into e power minus r by L into t. So this is the required response of the circuit. Okay. So the equation number 7 is defined as a solution for the first order non-homogeneous differential equation. So here we have two responses. Okay, two terms. So one term is a constant term v by r. So this is called as a steady state response. Another term is a exponential term. So it comprises of t. Okay, this is a transient response. Okay. So now the steady state response is also called as a forced response, and it is denoted by V by R. Already we have discussed, and this is mainly due to the applied voltage. Okay, so this response is also called as a zero state response. Similarly, transient response is denoted by the term V by R into e power minus R by L into T. Here T is involved. Okay, so this is a natural response of the circuit, which is also called as a zero input response, because it is a characteristics of the source free input. Source free means zero input circuits. Okay, so now we'll draw the graph. So T is taken along the x direction and I of t is taken along the y direction. So if we start from 0, if we substitute 0 over here, e power minus 0 is 1. So v by r minus v by r will be 0. So I of t is also 0. So if we keep on increasing the t value, the curve starts rising. Okay, exponentially it rises, and finally it will attain the steady state value. Say for example, if we substitute t is equal to infinity, so e power minus infinity will be 0. So I of t will be equal to v by r. So this v by r is a constant term. So this is also called as a steady state term. Okay, so it exponentially rises and attains its steady state condition. So steady state value is v by r. So this is the maximum value of current flowing through the circuit. So now if we take the point P, so at P, if we substitute, if we assume T is equal to L by R, here L by R by L into L by R. So these terms will get cancelled. So we will get I of t is equal to v by r minus v by r into e power minus 1. So on simplification, we will get 0.632 times v by r. Okay, so this point is defined as a time constant. Okay, so the point at which the current rises to 0.632 times the maximum value of the current under steady state condition. So here the maximum value of current is v by r under steady state condition. So now the time constant is given by tau. Okay, so tau is given by L by R. Okay, so this is the time constant of RL series circuit. So now we'll find out the voltage across the inductor. So we already know the formula, L into di of t by dt. So this can be written as L into d by dt of v by r minus v by r into e power minus r by L into t. So this is I of t equation. So now this can be written as L into d by dt of v by r minus d by dt of v by r into e power minus L by rt. Okay, so differentiating the first term will give you 0. So differentiation of the second term. So here we have e power minus r by L into t. So this is similar to the form e power at. So differentiating this e power at term, we will get a into e power 18. So similarly here we can apply. So first term is 0 minus, here v by r is a constant term. So differentiating this one, we'll get e power minus r by L into t multiplied by minus r by L. Okay, so r and r will get cancelled. Similarly L and L will get cancelled. So now we'll get VL of t is equal to minus v of e power minus r by L into t. So this is the voltage drop across the inductor. Similarly, we can find voltage drop across the resistor also. So R into I of t. So that is equal to V into 1 minus e power minus R by L into